Good morning everyone. We are discussing unit 3, that is uncertainty. Let us continue the same, that uncertainty. We already discussed in the last class what is this uncertainty. It's nothing but it refers to situations where there is a lack of complete information or knowledge about a particular aspects which leads to ambiguity and the unpredictability. And one of the way to overcome this uncertainty is the probabilistic reasoning. And in this probabilistic reasoning we have two methods. One is Bayes theorem and other one is a Bayesian belief network. In the last class I completed this Bayes theorem. Today in this session let us discuss about the Bayesian belief network, and with this with the help of this Bayesian belief network, how we are going to overcome the uncertainties. So what is this Bayesian belief network? It is a probabilistic graphical model which represents a set of variables and their conditional dependencies using a directed acyclic graph. So it is also called as a Bayes network or belief network, decision network, or simply we call it as the Bayesian model. And in simple terms we can also call this Bayesian belief network as BBN. And these networks are probabilistic. Why? Because these networks are built from a probability distribution and also uses probability theory for prediction and the anomaly detection. And coming to this real world applications, we know that they are probabilistic in nature, and to represent the relationship between multiple events we need a Bayesian network. And it also can be used for various tasks including prediction anomaly detection, diagnostics, time series prediction, and decision making under uncertainty. This Bayesian network can be used for building models from data and expert opinions, and it also consists of mainly two parts. One is directed acyclic graph, or simply we call it as DAG, and we need a table of conditional probabilities. So we know that graph means it consists of nodes and arcs. In the same way, when we construct a Bayesian network graph, it is also made up of two things. One is nodes and arcs. So this particular thing we call it as a node, and these directed graph generally we call it as the links. So where we call this each node in this particular Bayesian network corresponds to the random variables, and that variable can be continuous or discrete. So we know that when it comes to a classification model, the output is discrete, and when we are dealing with the regression problem, the output is continuous. So that random variable can be continuous or discrete depending upon the classification or regression problem. And this arc are directed arrows. These arcs are directed arrows represents the causal relationship or conditional probabilities between the random variables. And these directed links or arrows connect the pair of nodes in the graph. Yes, how we are going to pair these two nodes is with the help of this directed links. Then these links represent that one node directly influence the other node. Okay. So in this diagram we can see that there are four random variables A, B, C, D, E, which is represented by the nodes of this network graph. And when we are considering this node B here, which is connected with node A by a directed arrow, then node A is called as the parent of node B. This node A is parent of B as well as also parent of D, and where we say that C is the independent node. Node C is independent of node A. Why? Because there is no directed link between A and C. So just this representation we call it as the Bayesian network. And already told you this Bayesian network has two main components. One is causal components and actual numbers. That is, each node in the Bayesian network has conditional probability distribution, which we represented as something like this, which determines the effect of the parent on that node. And this Bayesian network is based on joint probability distribution and conditional probability. So before we are going to discuss about what is Bayesian network model, we should be aware of what is this joint probability distribution and conditional probability. Maybe you already learnt in maths what is this, but before going to discuss this Bayesian belief network, first let us understand what is this joint probability distribution and how it helps Bayesian belief network to overcome the uncertainties. See, joint probability distribution. So when we have multiple random variables like x1, x2, something xn, then the joint probability distribution represents the probability of different combinations of their values occurring together. So here this joint probability distribution can be written in this way in terms of joint probability distribution, that is probability of x1 given x2, x3, so on xn multiply into probability of x2, x3 till xn. So how we, in this equation, how we are going to read this one is the probability of x1 happening given that x2, x3 till xn have already happened, multiplied by joint probability of x2, x3 till xn. This is what we joint probability distribution. And in another way, how we are going to read this particular expansion is, see here, the probability of x1 given x2 till xn into probability of x2 given x3 and so on xn. It continues to probability of n1 in given xn into probability of xn. So what is this expansion? In this expansion, this particular probability of x1 given x2, x3 so on x1 is nothing but the probability of x1 given x2, x3, and this probability of x2 given x3 is probability of x2 given x3 and so on. This will continue. And then the last term, that is probability of xn, is the marginal probability of the last variable xn. So in general, this particular, for each variable, if you take instead of x1, x2, if you consider a variable xi, we can write that particular equation as probability of x1 till xn is equal to pi I equal to 1 to n probability of xi given parent nodes of that particular xi. Means that overall expression can be written in this form. This is called as the joint probability distribution. And here we know that, means to implement that, first we know this Bayesian network, this is a directed acyclic graph, simply we call it as DAG, where each node represents a random variable. What we discussed is xi, so it is random variable, and the edges represents the dependencies between the variables. And for each variable this xi, the set parent nodes refers to the immediate predecessors of this xi in the particular graph. And then next one is the joint probability decomposition. So instead of computing this joint probability directly, we can decompose it into conditional probabilities. That is, for each variable this xi, we compute probability of xi given parent nodes, the probability of xi given its parent nodes. So the product over all these variables gives the joint probability. So let me explain this with one example. Let's say we have three variables x1, x2, x3, and the Bayesian network specifies with these variables x1 has no parents, x2 has x1 as its parent, and x3 has x2 as its parents. Then the joint probability is decomposed as probability of x1, x2, x3 is equal to probability of x1 multiplied probability of x2 given x1 into probability of x3 given x2. Why? Because x1 is parent of x2, x2 is parent of x3. So in this way we are going to find out the joint probability. So whenever we are constructing a Bayesian belief network, the very first point is we have to identify the parent nodes of each variable in the Bayesian network. That is the first point. Then we are going to compute probability of xi given parent nodes for each variable, and then we are going to multiply the conditional probabilities to obtain the joint probabilities. So these 3 points are important when we are constructing a Bayesian belief network. So let us discuss with one example. This is one of the famous example for this Bayesian network. So here just try to understand the problem statement. Harry installed a new burglar alarm at his home to detect burglary. We know that what is burglary. So the alarm reliably responds at detecting a burglary, but also responds for minor earthquakes. Harry has two neighbors, David and Sophia, who have taken a responsibility to inform Harry at work when they hear the alarm. David always calls Harry when he hears alarm, but the problem here sometimes he got confused with the phone ringing and calls at that time also. So whenever phone also rings, he thought that there is an alarm, he calls the Harry. That is one problem with here. And other hand, Sophia likes to listen to music. So sometimes she misses to hear the alarm. So now here we would like to compute the probability of burglary alarm. So given the evidence who has or has not called, we would like to estimate the probability of a burglary. Is there any burglary or not? Given there is a alarm or not, whether David and Sophia calls the Harry or not. This is what the problem statement here. So now we are going to find out one problem for this particular problem statement using the Bayesian network model. So, with this problem statement, the very first thing is we have to draw the network. So here you see here burglary, earthquake are dependent on alarm. Why? Because when the alarm is going to ring when there is a burglary or earthquake, that's why these two are dependent variables on this one. And David and Sophia calls are dependent on alarm. So in this way we are going to draw the network. So when David and Sophia calls, when there is an alarm, and when there will be alarm, when there is a burglary or earthquake. So in this way we are going to draw the Bayesian network. And see here, for each node there is a table. That table generally we call it as a conditional probabilities table. Here what is we have true and false here, and see when we add true and false values, that should be equal to 1. That is the one condition for this conditional probability table in Bayesian network. So what is here? Probability there is a burglary is equal to 0.002. Probability there is no burglary is 0.998. Similarly here probability there is a alarm, okay, and David call is 0.91. Probability there is a alarm, David doesn't call is 0.09. In the similar way, same here. Similarly here, probability there is a alarm, Sophia called is 0.75. Probability there is a alarm and Sophia doesn't call is 0.25. And coming to here, when there is both burglary and alarm, there is a burglary, there is a alarm, that's why true values. The probability alarm ringed is 0.94. Probability alarm doesn't ring is 0.06. And how we are going to read this? There is a burglary, probability there is a burglary, there is no earthquake. Probability the alarm ringed is 0.95, and probability of there is a burglary, there is no earthquake. The probability of there is no alarm is 0.04. In this way, we are going to first create the conditional probabilities for each and every node. Based on this only, we are going to find out the probability whether alarm has ringed or not. And similarly here, probability there is a earthquake is 0.001, probability there is no earthquake is 0.999. Here, so as per that problem statement, now the question is, we have to find out, calculate the probability that alarm has sounded, but there is neither a burglary nor an earthquake occurred, and David and Sophia both called the Harry. I hope you understood this problem. Calculate the probability that alarm has sounded, but there is neither a burglary nor an earthquake occurred, and David and Sophia both called the Harry. So here, first we need to find the solution. For that, we have to find out, form a network structure. From that network structures and with the help of conditional probability tables, we have to find the solution for this particular problem.